2 minutes. Ready? Yes. Okay, we have 1 minute and we'll go in live. Sure. Any of your notes? Are you ready, Brett? Okay. So welcome back to the STEM Enhancement in Earth Science student presentations. Our next team is Earth from Space, Aerospace Engineering.
So, hi there, I am John Clemens and I'm from Shawnee, Oklahoma.
I'm Kayla Borlak, I'm from Mountain View, California.
I'm Anna McLennan and I'm from Cincinnati, Ohio. I'm Shivani Sani and I'm from Los Altos, California.
I'm Vinay Agrawal and I'm from Naperville, Illinois.
I'm Vibor Shrivastava and I'm from College Station, Texas.
I'm Audrey Safer, I'm from Richfield, Connecticut. This is Team Earth from Space and this is LegoSat.
So, the mission objectives for LegoSat. Our objectives were to develop an understanding about the fundamentals of satellite design and mission planning. They were to develop a working concept for a satellite that would operate as a test bed for future technologies and devices. And it was to propose multiple candidate experiments as prototypes for a future national high school competition wherein students could submit their own designs for instruments in hopes of testing them on board LegoSat. In conjunction with this, we hope to work with the LEGO Foundation to help fund this program and make it a reality.
So this is our conceptual design for our LegoSat. And let's first talk about some numbers. So the dimensions of the red carrier are 49 by 25 by 31 centimeters. And our predicted mass will be about 15 to 20 kilograms when it's fully loaded. And the volume would be 40,825 cubic centimeters. And for our subsystems, all of our subsystems will be located inside the carrier, and which will include the reaction wheels for attitude control, batteries for power, and the internal CPU. Our solar panels have 2 degrees of motion, so they can move along the y-axis and the z-axis.
Okay, now that we have a satellite design, what we need to do is we need to put it in orbit. We've chosen a low Earth orbit because its close proximity to the Earth's surface allows us for better resolution imaging. And our altitude will be about 300 kilometers. The inclination of this orbit, which we choose, determines the possible latitudes we can reach north and south. And one of our candidate experiments, the maximum latitude we need, is 60 degrees north and south, so that was the inclination we chose. We've also designed this model that allows you to calculate the field of view that each instrument has on a satellite, given its altitude and view angle, which is beta. With this model, we can have many applications, such as the single view, field of view. Here's some numbers for a 90-degree instrument angle calculation. The rounded field of view is the number for one single image of the Earth, the amount of surface area you can see. But other applications of this, such as the percent of area Earth covered per orbit, can give really interesting insights into how much your satellite will be able to see. So 5% is the amount of area of the Earth covered per orbit for this 90-degree satellite. Now that we have the satellite in orbit, we need to make sure that it is constantly nadir facing. And how we achieve this nadir point of orbit is by using 3 reaction wheels that cover along all 3 axes to make minor adjustments to the orbit. The satellite can get thrown off from its current orbit by variations in atmospheric density as well as particles in the atmosphere. And the inertial measurement unit, or IMU, aboard the satellite will be able to determine the orientation of the satellite at all times and decide what adjustments need to be made.
So the launch window that we designated for the LEGO set was from late June to early July of any given year. This is because in the months after this launch window would be the optimal time for all the instruments on board LEGOSat to observe their designated events. Now, once LEGOSat reaches orbit, it will enter a stage known as early operations. In early operations, this is essentially when the satellite boots up. So, the lithium-ion battery kicks in, the solar panels unfold, the devices turn on, and the satellite will reorient itself to face the planet in its proper position. Now, there is no specific launch time needed for this satellite, as the progress or the process of nodal regression would eliminate the possibility of creating a sun-synchronous orbit. Now, we estimate that the lifetime of LEGOSat would be 3 to 4 months. While this does not seem like a very long time for it to operate, it is more than enough time for our space grant. Simply, LEGOSat is a testbed. It does not need to operate for a full length of a normal satellite mission. So, we simply need to test the instruments and make sure that they can operate in space. Now, once the LEGOSat reaches the end of its life, it will enter into the atmosphere once again and completely disintegrate. Now, this actually does not contribute to the growing problem of orbital debris, therefore making it a pretty great satellite overall.
So the LEGOSat has the capacity to hold 6 candidate experiments, and in this presentation we have designed and proposed 4 of them. They are the Steve Aurora Sensing, Cloud Detection and Distinction, Earthquake Detection, and Wildfire Risk Assessment. And the great thing about these experiments is that many of them can share instrumentation, because they use a lot of the same imaging to achieve their objectives. Our first candidate experiment is one to image an aurora called STEVE, or Strong Thermal Emission Velocity Index. STEVE is a recently discovered type of aurora that occurs in lower latitudes than your typical aurora, like the aurora borealis or aurora australis. We propose to learn more about STEVE by imaging it in both the visible and near-infrared wavelengths. Additionally, since satellites are able to image over the ocean and other unpopulated areas, we may be able to use our STEVE experiment to learn whether STEVE has a longitudinal preference. The instruments we propose to use in the STEVE Aurora Sensing experiment are a spectrometer, because it will allow us to image STEVE in near-infrared. Imaging STEVE in near-infrared will allow us to determine if the broadband emission of STEVE extends beyond the visible range.
So the second experiment we're going to run on the LEGOSat is a cloud detection and distinction experiment. Clouds are important because they're vital to the hydrological system on Earth, which is essentially the water cycle, which is what life depends on. Furthermore, clouds are important because they manage the energy budget of the planet, which means they both trap greenhouse gases, which heats up the planet, and at the same time they cool the planet by reflecting UV rays from the sun. This dual identity of clouds causes some problems for meteorologists because they can't model they can't simulate the climates very well. So what this proposal will add to the data that we have on clouds so that meteorologists can gather all the data and find more models that are accurate. The best solution for detecting clouds is to use an infrared camera, since it can detect the heat signature of the clouds and be active at night, extending the time period which we can collect data. The problem with infrared is that snow and other forms of precipitation have similar heat signatures, so meteorologists could end up taking data from snow, which is not what they need data from clouds so they can create better models. The way we combat this problem is by putting a visible camera on board, which will take pictures at the same time whenever there's snow or sleet or anything that can be confused with clouds, heat signature-wise. So the camera will take 2 pictures, the visible one. So it'll take one, and then the second one it'll compare to see which is snow, which will be the one that will stay in the same position, versus the clouds, which will move as clouds move. This double check will help accurately determine the composition and temperature of clouds once the meteorologists analyze the infrared images. So I use the same infrared instrument as Anna used, which this infrared instrument will be used at all times when we find different clouds so that you can analyze it. And the visible spectrum camera will be used whenever the satellite passes over areas where the clouds can be confused with snow or ice. Again, it will take the two pictures, they'll be compared, and again, infrared images compared. And then the Arduino processor is basically like a micro CPU on board that tells the cameras when to take the pictures and stores them and relays them to the ground so meteorologists can analyze them.
The third experiment will be earthquake detection. So while scientists can usually pinpoint the location and magnitude of earthquakes, the time range estimated is often too broad for any evacuation strategies to be implemented. So this experiment strives to get that down to a few days based off of data collection. The first method, as seen in the top photo, is infrared light. The top image is the University of San Jose, where they actually found that crushing rock had to emit an infrared light. The second method in the bottom image is from the GOCE European satellite, which picked up on infrasound from earthquakes. The third method will be radio wave sensing, since that has the potential to sense earthquakes 1 to 6 days before occurrence. So the first instrument used will be an accelerometer. These accelerometers were also used on GOCE. Since the experiment is low enough, 300 kilometers, the same as GOCE, it can actually pick up on acceleration because the infrasound causes the atmosphere to vibrate, which accelerates the particles. I will also be using an infrared camera, the same one as Vibor and Anna, and then a radio wave chip.
Okay, so the next experiment that we're planning to fly on the LEGOSat is a wildfire risk assessment experiment. And basically what we're aiming to do is use a combination of red infrared and near infrared cameras in order to detect dry and arid areas. By detecting the normalized difference vegetation index, or the NDVI, we can figure out what areas are more dry and therefore more fire prone. Another potential benefit of this experiment is that we will have a visible spectrum camera on board. So we will be able to detect wildfires while they're still starting out. The benefit of this is that when wildfires are usually detected, they're observed from the ground, by which point they have the potential to become uncontrollable and therefore way more damaging. By using a visible spectrum camera and finding small fires from above, we have the potential to stop them before they get too catastrophic. So this experiment will require 3 instruments, the visible spectrum camera and the infrared camera as discussed earlier, in addition to the chameleon imager, which will be used to detect red infrared for the NDVI.
So the LEGOSat utilizes a power source known as a triple wing solar array. So this double-sided array operates in 2 degrees of motion. So if you watch what I'm doing right here, it will operate as rotating along the x-axis. Ample power for every single instrument on board, up to 80 watts. Now, these solar panels will actually fold up against the side of the LEGOSat, as you can see in that GIF up there. So, during lunch, during lunch, these solar panels will be folded against, and during early operations, the lithium-ion battery will kick in, unfold these solar panels, and begin electricity generation. And so, with this lithium-ion battery during early operations, it will also be able to be recharged. So, during times of zero sunlight, it will actually be able to power the satellite without the use of the solar panels.
So we will be using the Near network to transmit our data, and the Near network, or NEN, as a combination of ground stations located throughout the globe that allow us 10-minute passes multiple times a day. We will be using the X-band transmitter which has a downlink rate of 5 megabits per second. And if we combine that with the fact that there are 8 to 10 bits per byte, we can convert that to about 500,000 kilobytes per second. To find the total downlink, then therefore per 10 minutes will be about 300 megabytes, which will allow us to transfer detailed images and data multiple times a day.
So this chart provides the current data for our instruments as we know it. It includes volume, mass, power use, and data downlink. Strengths and weaknesses. So our satellite is very advantageous in the sense that it can support multiple experiments at once. So multiple missions and objectives could be completed. This includes the experiments that we've discussed, but it also leaves the potential for future experiments. In addition, this, like LegoSat, ensures the satellites that they're going to have a constant view of Earth, which for Earth-centric missions is particularly critical. In addition, while a short lifespan may seem almost like a disadvantage, it actually proves advantageous for us because it is just a limited time operation, and as John mentioned earlier, will eliminate orbital debris. However, there are still some things that can be improved by this experiment. We have an incomplete instrument data setting available, and our infrared camera has a very small field of view. Despite these challenges, we're still really confident in our solution and its ability to support satellites.
So at this time, LegoSat is completely conceptual, but in the future we hope to partner with the LEGO Foundation to receive funding to make it a reality. We'd like to partner with the LEGO Foundation to create a high school satellite design competition in which students would propose candidate experiments similar to the 4 you've seen here today. They would then compete to have their candidate experiment flown into orbit aboard the actual LegoSat. And the reason we propose to partner with the LEGO Foundation in particular is because the LEGO Foundation has demonstrated an interest in instilling a love of STEM in the next generation. For example, they have an EV3 robotics program. LegoSat team shares this goal of encouraging the next generation to go and follow their interests in STEM, particularly by learning about satellites and mission design. Thank you.
So we have a few people who we'd like to thank and just sort of share our reflections about the experience. So I feel there's a big difference between a concept and reality. And so I think being a NASA engineer has always been in the back of my head, but I never could have envisioned how fun and entertaining it would be to actually do the work and have a mentor who really cared and worked with us every day. I've learned a lot from my peers, and I'm really excited for pursuing an engineering career in the future.
Yeah, the SEAS program was great. It taught me a lot about the research and social aspect of engineering and how important that is if you actually want to get ahead. Dr. Fowler was a great mentor, and he taught us a lot about orbits and how you can combine it with the engineering process to get something real that can be applied.
I agree with both Vibora and Audrey. I had a really fun experience at SEAS and with our cool mentor, Dr. Fowler. And I also learned a lot about orbital mechanics and 3D modeling and things that I probably never would have done if I was at my house.
I enjoyed the SEAS program because it gave me the opportunity to learn a lot about the technical aspects about engineering and going through the whole design process from scratch. And in addition to that, it was also really nice to get to know people that were like-minded and had the same passions and interests as me.
I think my big takeaway from the SEAS program was learning a lot about the research and the whole process of engineering that goes into creating a satellite, because I'd never really had that experience before, and I don't think there was a way that I could have gotten it outside of this program. I really enjoyed working in a team environment because I learned a lot about how the actual design process works when you're working in a group and it's not just an individual project. And I also really enjoyed the opportunity to meet and interact with students from all around the country and learn why they're interested in STEM and interact with them about it.
I really enjoyed the SEAS program because of the in-depth work that I got to do with our project team. I really liked developing the model. It was this great process of trial and error that showed me that I can apply my skills and do something really cool and new with it that I don't ever get to see in school. And it was fantastic to work with my group. It was really cool to meet people that are from places of the country that I've never been to before, and just to combine all of our individual skills into a really cool final product.
So I'm not going to reiterate whatever you guys just said because I agree with every single bit of it. But I just want to thank all of you guys for making this an amazing trip. And you are all such incredible people, and it wouldn't have been the same thing without it. So thank you guys. Give yourself a hand.
So does anyone have a question for the aerospace engineering? Right here, Michael.
Okay, so I noticed on your cloud distinction program, you plan on including an Arduino unit. What's the intention of using an Arduino unit in addition to your standard CPU? Do you have a reason why you wouldn't just offload those functions onto your CPU?
We didn't want to load too much, and the function seemed simple enough that just loading would be.
Great. Congratulations to the team. So we'll pause for a moment while the next group is getting set up. Okay, our next team is Exploring the Moon team.
Okay, hello everyone. We're the Exploring the Moon team. My name is Isha Sharma. I'm from Chicago, Illinois.
My name is Katie Olson. I'm from Libertyville, Illinois.
My name is Garrett Stevenson, and I'm from Austin, Texas.
My name is Sierra, and I'm from Huntington Beach, California. My name is Olivia Pierce, and I'm from Easton, Massachusetts.
And our mission was to design a sustainable habitat for 5 astronauts for 6 months.
We'll start by explaining our landing sites and arrival plans, followed by a detailed description of our habitat and how it functions. We will end by talking about our scientific exploration missions.
So landing sites was a big topic of discussion in our group because we found 2 very similar craters on the opposite poles. However, we ultimately decided to choose Shackleton Crater, which is located in the lunar south pole. Here there is an abundance of resources and perpetual sunlight, but one reason we almost did not choose Shackleton was because of the low sun inclination angle. However, because we combated this problem because if you take the solar panels and rotate them with the sun, it fixes this. And our backup landing site we decided was Peary Crater, which is located at the lunar north pole, but we also chose Shackleton because it met more of our scientific objectives.
So before we talk about the specific mission timeline, it's important to talk about what rockets we're going to be using. For all of our supply missions, we chose to use Falcon Heavy rockets because their capabilities are already known. It's already known that they can take 17 tons of cargo to the moon, a number that we used in all of our planning. We also wanted to use a rocket that was already in use. However, for our manned missions, we decided instead to use the Space Launch System and the Orion capsule. We wanted to use an in-house technology because it's easier to control safety testing, and when we figured when astronaut lives were at stake, we wanted to use in-house technologies. Mission 1 is our first supply mission, and it's going to be where we take the actual main module of the habitat and stick it in the landing site. This will have all the furniture and life support machinery already pre-installed, but it won't have any of the supplies that the astronauts need for their journey. Depending on the weight, we might include some of the oxygen and nitrogen in order to pressurize the cabin before we even bring up the second supply mission. But we will also have our unmanned resource exploration rover, Scarab, which will begin to drill for resources, and our regolith concrete mixing rover, which will begin to make its tests on regolith concrete, which we need later in the mission. Mission 2 is our supply mission. This is where we're going to be bringing all of our tanks of oxygen, water, hydrogen, nitrogen, any sort of rovers, backup parts to machinery, and lab supplies. And then we also plan on bringing our space exploration vehicle, which is one of our rovers, and this has robotic arms which will hook up all of the tanks to our main module. This whole mission will fly in one capsule that'll land right next to our landing site, and then it will just stay there so that these tanks will have to be hooked up to the main module. And our hope is that 6 months after this, once we can have confirmation that all of our life support systems are functioning after the hookup, we're going to have our manned mission go, and that manned mission will take all of the food for the journey, all spacesuits, any sort of lab supplies that we left off of mission 2, things like seeds and gym supplies and things like that. And then this will come again on the SLS and the Orion capsule. And then mission 4 is our return mission home 6 months after this mission 3.
So this is the 3D model of our habitat, and as we progress through this presentation, we will now talk about its design and composition.
So first, for the wall composition, we have our walls are in the main hab able to be shielded from the 3 major problems which you face when you are doing space exploration, which are meteorite debris, space radiation, and hot and cold temperatures. So first, for our meteorite debris, we decided to use NASA's TransHab, which is a mixture of foam, mylar, Kevlar, and Nexstar. And it has already been proven to stop meteorites traveling up to 30,000 kilometers per hour, so we know that it is very effective. And it has the added benefit of being very light and easily compactable for launch. Next, for our insulation, we are using aerogel, which is also very light since it's made of 90% gases, over 90% gases, and it has been proven effective in insulating in very cold temperatures, which is very important for Shackleton Crater, where we are planning on landing. Next, our radiation is a combination of both high-density and low-density materials. So we're planning on using mainly polyether ether ketone, which is a type of plastic, and water as our low-density materials in order to help deflect cosmic radiation back into the environment. And for that cosmic radiation that is still pointed towards our habitat, we are going to use tungsten, which is a very high-density material, in order to absorb it.
So this is the design layout of our habitat. The circle on the left is the first floor and will be cylindrical shaped, and the circle on the right is the second floor and will be dome shaped. And the idea here is that all of the necessities that the astronauts need will be on the first floor, while the second floor will be used for storage. And to get between the floors, there will be a ladder and then a pulley system for lowering and raising boxes. So for the entrance of our habitat, there will be a pressurization system to adjust to the different environments, along with the storage for the suits. And the reason for this is because the dust from the regolith on the surface of the moon will get on the suits, and it's very hard to clean. So in order to minimize the amount that gets into the habitat, we combine these two systems. The bathroom will contain a toilet modeled after the one on the International Space Station, along with a shower that has 2 hoses, one for high-pressured outcoming water and one to suck up water that will minimize the amount of excess moisture in the habitat. And we will also have another backup toilet on site. The kitchen has the basic table and chairs, along with a hydrator, food storage, and water pump connected to the walls. The bedroom will both give and limit space because each astronaut is going to have their own little section. To give space, we have a bed that will fold up into the wall, similar to this one, except there will be no mattress because the 1/6 gravity on the moon does not need that comfort. So the gym area, because they need to work out 6 out of 7 days of the week for 2.5 hours a day, we put a bicycle, treadmill, and an advanced resistive exercise device, which is similar to a weightlifting device here on Earth. And for medical reasons, we will also have a table similar to the beds, as in it folds into the walls, along with storage for medical supplies for any medical emergency, and a vital monitor as seen in this photo.
For our lab wall composition, we decided to go with a mixture of an inflatable device, which is made of plastic, water, and plastics, and lunar concrete in order to prevent it from radiation and meteorite impacts. So first, for our lab structure, we decided to model our lab after the Antarctic lunar habitat that NASA has already developed in 2008 and 2009, so it's been tested to prove that it is effective in insulating from very cold temperatures. However, the only problem with this habitat is, as you can see, it's made out of plastic, so it doesn't really shield from radiation or meteorite impact. So in order to combat that, we decided to cover our habitat and our labs with 3 meters of lunar regolith called lunacrete, and this is lunar regolith mixed with sulfur in order to make it a strong concrete-like material. And we calculated that it would take about 51.17 kilograms of lunacrete to cover all of the labs and the tunnels. And we would do this by mixing it and extruding it using a 3D printing machine found in the KUKA robot, which would be mounted on a spider nut rover.
So we have 2 labs in our habitat. The first lab is the botany lab, whose goal is to experiment with growing highly nutritional and oxygen-yielding crops, because our eventual goal is to have this habitat be 100% self-sustainable with oxygen recycling, and we eventually want an agricultural section to grow plants as seen in the photo. And the second lab is the geology lab, whose goal is to experiment and collect rocks to find out the composition and history of the moon, especially focusing on the water ice found in the poles.
Power and communication, the backbone of any long-duration mission. Our primary power source will be 13,500 feet of solar panels, producing 60 kilowatts of energy. We will use that energy to power the habitat and charge batteries that will be used when the solar panels aren't in the sun. The most optimal position to place our solar panels will be 10 meters off the ground, so they can have the most time in the sun and facing directly towards the horizon because of the sun's low inclination angle on the poles. They will also be placed on gimbals so they can follow the sun as it shifts across the horizon. Our secondary power source will be NASA's kilopower nuclear fission reactors. We will bring 3 of these, each producing 10 kilowatts of power. They will be used to power the habitat assisted by the batteries, while the solar panels are offline and shaded, and can also be used in an emergency where there's a solar panel failure or a battery failure. We will store power using a series of 24 lithium-ion batteries. They will be charged by the solar panels during the day, and when the solar panels are shaded, they will discharge all that energy. They can also discharge their energy during a power failure or emergency situation. We'll communicate with Earth from our habitat and vice versa with optical communication. Optical communication works by having a data center, sorry, I forgot the word, that converts all the digital data that it receives into pulses of light at the wavelength of 1.55 micrometers, which represents binary. And then once it travels to the receiver will use a system of lenses and mirrors to convert that back into digital data and send it to where it needs to go. The pros of using this technology rather than microwaves would be that they travel faster and can carry more data than microwaves. But some of the cons are that atmospheric interference, such as clouds, can block the signal, and it requires a very high level of precision.
Currently, life support systems on the International Space Station are maintained by the Environmental Control and Life Support Systems, or the ECLSS. This is a multi-part system that keeps the pressure, water, oxygen, and waste recycling and moving throughout the International Space Station. We plan on using almost the exact same life support system. However, we had to make a few adjustments because our base does not receive any resupply missions throughout the duration of the stay, and our base is far bigger than the International Space Station. Our main adjustment is that we have to have 3 oxygen generation systems. These oxygen generation systems use electrolysis in a Sabatier reactor to get oxygen out of water and water out of carbon dioxide. And then this is used in tandem with the air revitalization system, which circulates that oxygen throughout the cabin and removes any carbon dioxide and contaminants from the air. As for our atmospheric Earth-like conditions inside the habitat, we need to maintain the 70-30 ratio of nitrogen and oxygen. We quantified those using our volume measurements there, which will keep the pressure constant with Earth pressure. And then this oxygen that we breathe in will be recycled and can be used. However, for this recycling process to be 100% efficient, where we don't lose any oxygen, we need to bring along hydrogen to keep this recycling going. We will also bring along 95 kilograms of water to be used purely for electrolysis, so oxygen oxygen generation through electrolysis, and this was enough to sustain for 2 weeks. So in the case where this recycling system doesn't work for some reason, we have 2 weeks of contingency oxygen through electrolysis, and then we also have enough solid oxygen tanks to sustain our crew for an additional 1 month in case both systems fail for some reason. As for our water resources, we plan on bringing about 1,500 kilograms of water to be used for consumption, insulation, labs, and any other machinery. The current water recovery filtration systems on the ISS are 88% efficient. However, we couldn't assume 88% efficiency because our base is much larger and can't retain things like sweat as easily, so we assumed 80% efficiency for our calculation purposes. As for food, each astronaut eats about 2.5 kilograms of food per day on the International Space Station. We kept this number consistent, but we decided to bring along 2,500 kilograms of food so that we had a few extra weeks of food just in case something went wrong with the return mission. We do have a botany lab aboard, but we decided that it wasn't safe to rely on this for food because we don't know how plants will fare in lunar gravity because there hasn't been any experiments done on that. As for our waste, any non-converted waste will be vacuum sealed and contained, and then this containment module can be jettisoned during the return rocket home. And then as for our temperature and humidity control, these will be controlled by multiple ventilation fans, a low temperature cooled hydrophilic coated condenser heat exchanger, and a rotary liquid separator, which can remove excessive moisture from the air. We'll also have a series of air ducts fitted with air filters to remove any dangerous particles or contaminants from the air. These filters will have to get changed out. And then this temperature and humidity control system will also be linked to our fire detection technology, which is just basically smoke detectors. We decided not to rely on any lunar resources for this beginning mission because we decided that in the case where we couldn't extract or utilize resources from the lunar surface, we didn't want to leave our astronauts stranded. So we decided that we wanted to use these resources more in the future to make our base more self-sufficient. Some of these resources that we plan on using in the future include helium-3 for nuclear fusion power, water ice for consumption purposes, oxygen generation, and potentially rocket fuel, rare earth metals for certain technologies, and then also we do plan on using the lunar regolith, as Sierra stated prior to this, for our lab walls. However, this is not necessary to make our labs, it's just an extra precaution.
Rovers are invaluable for research in space, but they often come with the drawback of being very heavy. And as we were reminded, mass equals money. However, we decided that the benefits outweigh the cost for these 3 rovers. Our first rover is the Lunar Electric Rover. It is a manned rover with a pressurized cabin capable of sustaining 2 astronauts for 14 days for an EVA, or 4 astronauts for 72 hours in an emergency. Having a pressurized cabin allows it to be able to have a range of 125 miles from the habitat, which means that crew has a much bigger area to explore on the moon. It is also a good safety precaution if anything happens to habitat. Our next rover is Scarab. Our next rover, Scarab, is an unmanned scientific rover that is equipped with a resolve drill. It is able to complete in situ resource utilization objectives, which means it is able to drive distances, drill, collect, and analyze samples. It is also designed for cold, dark, steep, and cratered areas, making it perfect to search for helium-3 and water ice in permanently shadowed areas. Our final rover is in a conceptual stage. In order to complete our objective of using sulfur concrete on our habitat, we need to have a tool that will be able to heat, mix, and pour the sulfur and regular concrete mixture. In order to do this, we have an idea of using a spider-knot rover with a large mixing oven, similar to the oven subsystem on the proposed resource prospector, or system modeled by the sulfur concrete contour crafting's KUKA robot.
So we identified 5 scientific objectives in this project to maximize our scientific basis of Shackleton Crater. And so the first is the potential of water ice. As Katie mentioned, Shackleton Crater, the base of Shackleton Crater is estimated to be covered with 22% water ice, which could be used for future missions for either fuel, as Olivia mentioned, or as a water resource. We also want to assess the presence of other polar volatiles, which are lightweight gases such as chlorine, nitrogen, and most importantly, helium-3. As Olivia mentioned, helium-3 can be used for nuclear fusion, and it is not found on the Earth, so it could potentially be used in the future for resource mining, which makes it a very important resource on the moon. Thirdly, we would like to sample the crustal variation of the walls of Shackleton Crater, because Shackleton Crater is located on a massive or a large hill in the moon, which allows it to have cut very deep into the crust of the moon, allowing for geologic sampling to reveal more of the history of the moon. We'd also like to sample the ejecta, or what comes out of the crater, as this could help us date the South Pole Atkins Basin, which is a large crater on the south pole of the moon. Finally, we want to test a 7-day manned rover trip to both Slater and Faustini craters in order to both test the capabilities of our rovers to ensure that we can do multiple day long-term trips, and to sample young craters in Slater crater as well as perennial cold traps in Faustini crater.
In the future of our habitat, we would like to create outposts in order to resupply the necessities for longer EVAs, which would allow us to be able to explore the far side, more of the far side of the moon and Munson crater. We would also like to utilize a 3D printing rover to be able to create further habitats on the moon. In addition, we would like to explore lava tubes and volcanic activity, create sunlight redirecting satellites, and create an astrophysics lab on the far side of the moon. Finally, we would like to thank all of the CE staff who helped us and made this internship possible, especially our mentor, Dr. Iacobino, our proctors, Mr. and Mrs. Luera, and Ms. Hanover. This internship has been a very invaluable experience to me because of the hands-on experience I got with research in aerospace, space research, and also the interaction I got with experts in real-life interaction I got with experts in this field.
This internship was really special to me because I got to learn a lot about the different practical skills in a realistic engineering situation, and I also will be forever grateful because I made a lot of lifelong friends here.
By participating in this internship, I was exposed to a plethora of opportunities and experiences that I never knew existed. This internship has definitely opened my eyes to a bunch of other career paths and opportunities I can explore in the future.
This internship really taught me so much about how interdisciplinary engineering really can be. Before I came into this, I thought engineering was all about, making sure that the habitat's designed correctly and all the math and everything, but we ended up using chemistry, biology, physics to just discover all the different areas and aspects of our habitat, and I found that really interesting. And like Katie said, of course, it gave a great opportunity to meet all these amazing people from all over the place and make lifelong friends.
Because of this project, I definitely realized how important it is to look into the minutia and details of any sort of even hypothetical project, and how sometimes you look at a small problem and you're like, oh, this is going to take me 10 minutes to solve, and 10 hours later you're still working on it. So that, it was really invaluable in that way.
Yeah, so now that we're done with our presentation, are there any questions?
We have one question.
Yeah, could the moon ever be profitable? And if so, what would NASA's role be?
So, do we want to tackle this together?
Let's do it.
Okay, so yes, definitely. As Sierra mentioned, the helium-3 that's on there, if we could figure out nuclear fusion from it, it would become like world-changing, because that's a strong source of power, and because when you do nuclear fusion, you don't get the radioactive byproducts that you get when you do nuclear fission. So it would totally reinvent the global energy scene. So because no one can own the moon via the current UN law, I don't know how it's going to work when we start mining there, and whether NASA's going to be the seller, or whether I know Jeff Bezos and Elon Musk have both expressed interest in establishing mining colonies to mine helium-3.
Yeah. So NASA's definitely looking into it. A lot of private sectors, so SpaceX and Jeff Bezos recently announced that they're actually going to the crater that we picked, Shackleton Crater, to potentially do resource mining. And so it's something that is very real in the future, and not just helium-3 like Olivia mentioned, but water ice for hydrogen fuel and other resources. There's rare earth metals like titanium on the moon, are very important to be used here on Earth.
There are also some people who think that surrounding the moon and solar panels and beaming the energy back to Earth could happen, but wait a century or two and you'll see.
Okay, please join me and thank you. We'll get one. Our next presentation is by the Emergency Preparedness Team. Hold for 1 minute. We'll be live. We're ready.
Good afternoon, everyone. We're the Emergency Preparedness Team, and for the past 2 weeks, we've been looking into the Bastrop County complex fire in 2011, which was Texas' deadliest wildfire. And we were analyzing vegetation regrowth and comparing it to burn severity. I'm Ajay Jayaraman from Dunlap, Illinois.
My name is Ethan McFarland from Colorado Springs, Colorado.
I'm Asha Karmakar. I'm from Austin, Texas.
My name is Iris Down. I'm from Cupertino, California.
I'm Sean Yang and I'm from Houston, Texas.
I'm Fiona Pollock and I'm from Philadelphia, Pennsylvania.
My name is Pranav Rajan. I'm from Lincoln, Nebraska. Alright, so although death and destruction are common names or words that are accompany wildfires, wildfires actually play a really influential role in our day-to-day lives by affecting our surrounding environments. Wildfires occur naturally in many forest ecosystems and serve to regenerate our environments through clearing flammable undergrowth, accelerating the carbon cycle, and thinning older trees, while simultaneously replenishing soil nutrients and fertilizing soil. So while researching the effects of natural wildfires, scientists discovered that multiple factors play into the regrowth, and that's really what we looked into, is what factors are changing the rate at which items or vegetation is regrowing after a wildfire. So remote sensing techniques proved to be a useful method to do this and quantify burn severity and the regrowth that occurs after a burn, mostly because it provides scientists with an efficient way, while unlike field studies, which are extremely limited to small areas due to the fact that we lack manpower and resources. Remote sensing uses satellite imagery, which allows for a holistic analysis over like a general area, and it's just much more efficient. So Landsat multispectral imagery, by using Landsat multispectral imagery, we were able to calculate indices, and these indices essentially enabled us to quantify the correlation between burn severity and burn regrowth. So the data also suggested that there is a relationship between post-fire vegetation and recovery and the climates in temperate ecosystems of Western North America. So these methodologies can also be cross-applied to a variety of wildfires, not just the Bastrop County complex wildfires, regardless of their intensity or how widespread the fires were. The aftermath of these wildfires, we also discovered, depends on a variety of environmental variables, including species, soil composition, weather, and seed production. So those were the main variables we researched, and considering the impracticalities of going into the fields and studying large areas that were burned through field work, due to the lack of manpower, like I said previously, remote sensing through satellite imagery allows for a more general overview, like I said, of an entire region and the opportunity to calculate those indices, which enable us to create conclusions that are more specific and enable us to create better understandings of the fire and how vegetation is regrowing. So once again, our project focused on the Bastrop County complex wildfire, and Fiona will speak a little more about that.
Thank you. So I want to just introduce you a little bit better to the geography and climate of the Bastrop region specifically, which is the area that we examined, and particularly the conditions in this area that made it so susceptible to the propagation of wildfire in 2011. So if you look at the land cover map on bottom, what you see in Bastrop is that dark green area, which indicates a heavily forested region, surrounded by the lighter green, which is more sparse vegetation like fields of rush. And then on the western edge of the forest there, you have the pink area, which indicates the town of Bastrop itself. So what was this area going through in 2011? Well, it was Texas, so it was really, really hot. In fact, it was the hottest United States summer on record at the time, with an average temperature of 86.8 degrees Fahrenheit. It was also the most extreme drought since the 1950s, and an average rainfall of only 14.88 inches. So really, really hot and really, really dry, which is ideal conditions for the propagation of fire. At the same time, you had Tropical Storm Lee moving up the Gulf Coast of Texas, which brought winds of over 60 miles per hour, which kind of accomplished two things. Number one, we think that may have been the catalyst for the original start of the fire, blowing down the power lines that ignited the spark that lit the fire. And also, having such strong winds made it really, really easy for the fire to spread down south across the forest of Bastrop. So in terms of the fire itself, it actually started as 3 smaller fires that eventually spread down south across the forest into one major conflagration that spread for over a month in the forest and into the east of the town of Bastrop before finally extinguished in late October 2011. So as you can see in the time series here, we have 2011 all the way on the left, and 2013, 15, and 18. And what you can see is a really, really severe burn scar at the start that eventually fades, but it doesn't really fade completely, and it fades variably over time. So that's going to be the bulk of what we talk about today, is how the vegetation recovered and regrew in these different areas at different speeds. So in terms of the fire itself and the damage and losses, it took a heavy, heavy toll on the state of Texas. It was the worst wildfire in Texas history, with over $325 million worth of damage and 2 human lives lost. So this kind of really affected everything in the Bastrop area. So it wasn't just the ecosystem, it wasn't just the infrastructure, it also really greatly impacted the human population, and it pretty much impacted every aspect of life in Bastrop. So the recovery that we really want to talk about here is specifically with regards to the ecosystem and with the low-volume hunting. So the bulk of our presentation is about the vegetation regrowth, so we're going to kind of be talking throughout the presentation about a couple different recovery efforts and trying to replant some of the forests that were burned down, as you saw in the original burn scar, which leads to our project goals overall. So the immediate aftermath of the fire and the immediate burn scars and damage was pretty well mapped and analyzed in the couple years after the fire, and that's some of the original literature that we were building off of. But with this project, we really kind of wanted to go into a more long-term study of how the vegetation would be recovering over time from 2011 to 2019. So in this project, we wanted to research and analyze the general objective long-term effects of the Bastrop County fire, but then we also wanted to kind of go more in depth with our analysis of the relationships between a couple variables, most specifically the bird severity, which we're going to be talking a lot about, and the vegetation regrowth, and also the environmental factors that may have accounted for the differences in vegetation regrowth that we observed in the study.
So to investigate our project goals, we employ remote sensing techniques in our data acquisition and analysis process. Unlike field sampling, remote sensing through satellite imagery is able to survey large areas that would otherwise be impractical. We use multispectral surface reflectance imagery from NASA's Landsat 5 and 8 in near-infrared, shortwave infrared, and visible red bands. To reduce the variability in choosing our dataset, we considered several criteria, including image quality, cloud cover, and time of year. Image quality and cloud cover simply ensure that enough data is extractable, while the time of year ensures that variations over time are not simply due to any seasonal fluctuations that may occur. After applying these criteria, we obtained our satellite imagery from the USGS Earth Explorer online database. We used two main indices to quantify our data. Firstly, DNVR stands for the Difference Normalized Burn Ratio, and NDVI stands for the Normalized Difference Vegetation Index. Both are common indices used in remote sensing calculated with spectral bands from the satellite imagery. So, DNVR is the difference between pre-fire NVR and post-fire NVR, which quantifies the burn severity after a fire. The NDVI, on the other hand, quantifies vegetation regrowth, which is useful in assessing plant recovery. Using QGIS, which is a geographic information system, along with Python scripts and the DNVR and NDVI indices, we process and produce several examinable figures. First, we clip the original satellite imagery to only the burn region. Second, we calculated a map of the region overlaid by the values of DNVR. Thirdly, we reference the standard DNVR thresholds while examining the frequency distribution of the DNVR data points. Then, we calculate the NDVI map for each day and each burn severity. With this, these figures then allow us to analyze the correlation between burn severity and vegetation regrowth, which Iris will now expound.
Okay. Now onto our vegetation regrowth analysis. So like Sean said, the first indice that we used was DNVR, which is the burn severity. And so using this, we were able to generate these different thresholds that show the different amounts of burn severity throughout the burn scar. So this we have here is a heat map. So basically, okay, so for a heat map, we took a map of the burn scar and we basically overlaid all the colors onto it. So each of the color represents different burn severity. So starting from green, which is unburned, to red, which is high severity. And so some things you can know about this picture is that the burn scar shape itself is like a triangle. And this is because the fire started in the northern vertex, and because the wind was blowing towards the south, it kind of spread the fire out, just like how pressure waves spread out in water. Another interesting thing to note is that there's a vertical band of red towards the middle. And you can see that's because that's a very high severity fire, and it's because, again, the wind was blowing in a southern direction, and that spread that out in the vertical line. So the other indice that we really looked at was NDVI, which is used to categorize the amount of vegetation regrowth. And so what we did was, using all the Landsat images that we had, we calculated the mean NDVI for each image, and we did plot that over time. So that's what you can see on the screen here. The x-axis is all the individual dates that we selected, and the y-axis is NDVI scaled to 1,000. And so using this graph, we can see a pretty clear general trend. So starting from about 2009, which was our first data point, there's a clear decline, and that's due to the drought that Fiona was talking about. And then there's a very clear decrease at 2011 because of the fire. So that makes sense. If there's fire, then the vegetation goes down. And then from there, what's interesting to know is that the regeneration actually happened fairly quickly. So around 2013, you can see that the levels of NDVI go back to around the pre-fire levels, and it stays there for pretty much until 2018. And so this might be a little misleading by itself, because when we did the field investigation, we could see that there's still a big difference between the unburned and the burned areas. And so it's likely that these high NDVI values may have been caused by just regrowth of lower shrubs and not of the tall level pines that we're looking at. And so this shows us that the land itself is healing, but that is not growing the tall trees yet. And in addition to this main trend, we can still see some fluctuations. For example, in 2015 up there's another decrease, and this is because there was another wildfire that was happening around this area, but they were very hot and dry conditions. And a very similar situation happened in 2018. So in addition to looking at the main trend, we also looked at the burn severities for each of, for the NDVI for each of the burn severities. And so using similar colors from the heat map, we have the green being the unburned up to the red being the high severity. And so with these 4 lines, what's interesting is that it follows the main trend, but there's also more fluctuations. For example, the green and the yellow, which shows the unburned and the low severity, they fluctuate a lot more. And so this shows that perhaps because they were less burned, they're more responsive to changes in the environment. And another interesting thing is that we have this kind of plateau around 2011. And so this can be attributed to some human recovery efforts that cause a delay in the vegetation regrowth, but then also just because we ordered our days ski regularly, so there might be some error. And the last graph we made here is a bar chart that directly correlates NDVI to vegetation regrowth with NVI to burn severity. And so what we have on the y-axis here is actually the percent change in NDVI. So the first cluster of days from 2011 to 2013, it shows very clearly the quick recovery. So you can see that with higher burn severity, which is the red, we actually have the highest change in NDVI, which is consistent with other findings. The second cluster shows a similar trend, although the NDVI growth is not quite as large because of a smaller time frame. But most interesting is that from 2016 to 2018, which is our most recent one, the NDVI values actually reached a plateau. And so this tells us that perhaps after a certain amount of time, the burn severity levels may no longer impact the amount of NDVI change. And this is really important for looking at other wildfires in the western United States.
So as a part of our research, we actually traveled to the Griffith League Scout Ranch to conduct the field investigation. And as part of our field investigation, we were given 4 points to survey by our ranch guide, Ms. Jessica Snyder. And 3 of these points were located in the burned area of the ranch, and 1 was located in the unburned area. So we wanted to observe how certain geographical features directly affected vegetation regrowth in these areas. And to do so, we isolated 4 more points in the ranch region that had similar geographical features to the points that we actually surveyed, but this time they all had similar NDVI values before the fire took place. This way we could analyze how starting from a similar point, vegetation regrowth differed in areas with varying geographical factors. And so if you look at the graph, you can see that throughout 2010 and mid-2011, all of the NDVI values of the points experienced a steady decline due to drought. And when the fire occurred in September of 2011, the 3 unburned points, their NDVIs dipped sharply while the unburned continued to decrease steadily. And the point B, the burned area, which was not replanted, and the trees were removed by a company called Go Green, which came and removed the dead trees in the area. This area has significantly slower vegetation regrowth than points C and D, where the area remained undisturbed. This is due to the fact that heavy machinery from that company compressed and disturbed the soil and damaged remaining vegetation. So here we have some images that we took during our field investigation. The one on the top left is just the burn area where without tree removal, and you can see the brushy regrowth in the area and the remains of dead pine trees. Under that we have the burned area where the tree removal did occur, and you can see the upturned dirt and the area that was damaged by the heavy machinery. Next, we have the burned and unburned boundary, and this is a particularly interesting image because this is the exact point at which the burned boundary was. So you can see the difference between the matured forest in the unburned area and the secondary succession and brushy regrowth occurring in the burned area. And lastly, we have our unburned area where the pine trees are still remain and is heavily vegetated.
So now that we had surveyed control points that were representative of burned and unburned areas, we decided to shift our focus as a group to revisiting the original research questions that helped to illustrate the broader applications of our research. Some of our primary areas of interest included evaluating the long-term recovery of the wildfire, analyzing the relationship between spectral measures of vegetation regrowth and burn severity, and then also any environmental factors that may account for discrepancies in the NBI change that we're seeing. In order to answer these questions, we referenced the graph that was displayed earlier, which charts NDVI change by burn severity class. In doing so, we found that both satellite analysis and field investigation were successful in validating the expected contrast between measures of burn with different levels of severity. In particular, areas of high burn severity tended to experience greater changes of NDVI, but this trend may only be temporary because it tended to level off over time. We also observed that while the NDVI time series indicated a rapid rate of recovery, the count and form of vegetation growth still lagged behind the unburned plots. To explain the reasoning behind the longer rebound period for the lovely pine species, it is helpful to consider that the sheer size and scope of the wildfire may have paved the way for a competing tree species to take over. At a qualitative level, certain natural and anthropogenic factors, such as replanting initiatives and the prevalence of nearby water sources, may be correlated with faster regrowth. On the other end, however, targeted logging efforts through the Go Green initiative appear to be adversely linked to forest health. In the wider picture, this understanding of how field methods can be integrated with remote sensing techniques will lay the foundation for deeper research into the types of environmental factors that affect vegetation regrowth, which is a topic Ajay will now expand upon.
Yeah, so for the past 2 weeks, we've been working on building upon past research into the Bastrop County wildfire, particularly as everyone has been talking about the relationship between NDVI and the burn severity. So in past research, many results have been inconclusive because due to the lack of since not a lot of time has passed since the fire, they were unable to draw conclusions, as I said. And now that we're expounding on their research, we are kind of updating and trying to yield some more further analysis. But there are some things that we wish we could have done better to have yielded more statistically significant results, particularly involving a control group. This one control group that we would have liked to do would be involving the unburned region rather than the burned region, and trying to set it up as the control and using it to compare with the variety of points that we had picked otherwise. And other than that, we also wanted to investigate some preventative measures. Pranav mentioned this in the beginning, but wildfires are actually a naturally occurring phenomenon. So now that humans have kind of taken over the area and are preventing them from naturally occurring, underbrush grows and can lead to large amounts of sort of tinder for wildfires existing. And because of this, a popular solution has become known as controlled burns, which is lighting purposeful fires within the forest to sort of clear out this underbrush and make sure that the larger wildfires like the Bastrop County wildfire does not occur. So, in fact, there is a controlled burn planned in the region that we visited for our field study, the Griffith Park, and this controlled burn will happen in the next couple of months. So, using the different techniques that we've used in the past 2 weeks, we could potentially examine the effectiveness of such a controlled burn or better locations for controlled burns in the future. Along with that, you may have heard a couple people mention some different things that were issues when looking at NDVI values, particularly Iris mentioned earlier, that has to do a lot with the satellite that we're using, Landsat. Because Landsat doesn't have an extremely high resolution, when we see 1 pixel on a Landsat screen, it actually correlates to a 30-meter space that you can't tell like what tree is theirs, or difference between canopy levels, underbrush versus undergrowth versus overgrowth, and different factors that we weren't really able to observe that we actually noticed when we went out into the field. Some other things that we noticed were involving the different tree species and how that affected regrowth, and how some trees, like the lullaby pines, were naturally regrowing after the fire, and others were being replanted through conservation efforts. And overall, this is also very significant towards the planning of controlled burns. So, just to conclude, we've spent the last 2 weeks to look into the Bastrop County wildfire, and we've really been able to draw some conclusions, but we have to thank a couple people that got us here, especially our mentor, Miss Teresa Howard, and Miss Margaret Baggio, for making this all possible. Sorry, I'm stuttering. And we'd all like to say a couple words to talk about our experience here. Personally, I come from a place where I'm I live with a lot of like-minded students, and I've seen the same thing here, but here I see a very dedicated group of individuals that cares about the different aspects of STEM, and they sort of come together in a unique way that I've never really seen before. And I really like that aspect. And then on the more technical side of things, I got to enjoy our field investigation, which in the moment seemed like torture, but afterwards, looking back on it, it was a lot of fun.
I think the most valuable aspect for me is that there's a stigma that tends to be conflated with lab research and many scientific disciplines, that there's just such a high barrier of entry that it's an area that people don't want to get into. And I think this program is an effective way to just gain exposure to different industries and what might appeal to you personally. And I think nowhere is that exemplified most clearly, or more clearly than in remote sensing, where using just your smartphone, you can scale the face of the earth and observe these trends that are really larger than life. And so for me, I think it'll help me orient myself as I pursue a career in GIS, or just look into researching what I want to do in better detail.
Well, for me, I'm just very grateful for this incredible opportunity. I was able to work with so many talented, like-minded students, and have the opportunity to also be mentored by scientists who are deeply involved in their field. And I came into this program with mostly a background in computer science. I really didn't know much about earth science, and in these 2 weeks, I've just learned an immense amount of information, and a lot of it's so interesting. And I think this program has really helped me to decide what direction I might want to take my career in.
Okay. Well, for me, basically, I think I'm lucky enough to come from an area where there are a lot of computer science and a lot of computer engineers. So for me, having my interest in remote sensing and earth science and natural sciences, I was always part of a minority back at home. So coming here is really cool to see all these people who have the same interests as me, and to really reinforce my beliefs that I want to work at NASA and I want to do mission control. And of course, we all know the team bonding side has been a lot of fun with our group. We've all had our experiences working QGIS in the wee hours in the morning. It's really great to really be friends with these people that come from so many miles away from you, and I think it's been a really great experience.
So, one of the most meaningful aspects of this program to me was the opportunity to collaborate and make friends with other people on my team and all the other interns that share very similar interests to what I like, and everyone here who all possess the initiative and the skill to see their plans to fruition. What I didn't expect was that the same sort of initiative would be actually one of the stumbling blocks that we face. So each team member on our team took the initiative to raise many concerns and inputs. So one of the challenges that we actually faced was compromising between everyone's differing but definitely reasonable opinions. Despite this, all of the interns in this program have been extremely friendly and willing to communicate. So all of our, a middle ground usually only required some brief discussion. And from this internship, I have improved my research and coding skills while greatly developing soft skills like teamwork in tough situations.
For me, I think what I'm getting out of this internship is really going into it, especially in the first couple of years of high school, I was really much more interested in the hard natural sciences, hard earth sciences. I just wanted to do something, that was it. And then especially coming out of this is really going to help me as I'm pivoting in a new direction going into my junior year. I did a lot of the mapping in this project. I worked a lot with GIS and geography, and those skills that I learned here are going to help a lot as I work next year to try to get much more into urban geography and environmental justice, which is something I want to try to focus on next year. So this is going to help me a lot as I move in a new direction academically.
Something I feel like that lacks in high school education and institutions is the application of learned skills. I believe that's what leads to disinterest in students in certain subjects. And I appreciate NASA Seas for providing me with an opportunity where I can apply the skills I've learned in my schools, whether it be computer science or remote sensing. I feel like this internship has enabled me to apply those skills in a real life setting where I can see the true application of what I've learned in school. I believe that's what's important when it comes to just education in general, and it's something that I feel we don't get to do a lot of in high schools,
we mentioned her earlier, and we'd like to do another larger thanks for Ms. Howard. And she's been like invaluable to us, and she's like really gave us the freedom to explore QGIS and like all these different tools and help us through all the struggles that we have. So like, if possible, could you come up here quickly? We have a small party gift for you, and we're really happy with you.
Any questions? No. We're gonna take a question from another individual. Any questions from this side of the room? If not, we're over our time limit, so we're gonna